what we're going to do is we're going to start looking at those last two sections. It's going to talk about friction, air resistance, gravitational force, and I don't have it on here, but it's going to end up looking at that last section being centripetal forces. Well, when we think of Newton's first law, okay, think about what it states. It says that objects in motion tend to stay in motion and objects at rest tend to stay at rest. Well, if this is true, then why don't all objects continue in motion forever? Well, the reason is going to be because of friction. And friction is just going to be any force that opposes the motion of an object. Meaning that if I'm moving left, friction's going to act right. If something is falling, friction is going to be acting upwards. The result of friction is going to be the two surfaces that are rubbing together is always going to end up producing heat. There's going to be two factors that friction is going to depend on, or two factors that are going to affect friction. Number one is going to be the types of surfaces, meaning that if I take an object and I slide it across the floor, and I take the same object and slide it across ice, you're going to find out that there's going to be different amounts of friction. And the second one is going to be how hard those surfaces push against one another, meaning that if I take my hands and I lightly rub them together, I really don't feel much. But if I really push my hands hard together, you're going to find out that there's going to end up being a lot more heat. Is friction good? Depends on what we're trying to do. I mean, if you think about the other day, you think about Boston, New York, things like that, places that are getting lots of snow. Well, in places where it's hard to stop, what do? They go ahead and they put out some sand, they put out some gravel and things like that. What they're trying to do is they're trying to intentionally increase the amount of friction, causing more traction. Meanwhile, on the other hand, if you're thinking about an automobile, all of the moving parts and things like that, in that case, friction is going to be bad because it's going to reduce our gas mileage or reduce the efficiency of that car. There's going to be three types of friction. The first one, well, I talked about automobiles, okay? The first one's going to be fluid friction. That's the reason why we put oil in our cars. All of the moving parts, those parts rubbing up against one another produces a lot of heat, causes a lot of inefficiency. So we put oil in there to cause those parts to move by one another a lot easier. The second one's going to be, well, that's kind of without the oil. That's going to be sliding friction, where the two surfaces are actually rubbing against one another without anything in between. And the last one, well, that's going to be what we did in the lab. Okay, that's going to be our rolling friction. You know, it's the friction that occurs when an object rolls over a surface. If you took your car and just put it on the floor and you lit that string and caused that string to burn and all of a sudden that weight went across, I don't know if your car would move. Might move a little bit with the 3 rubber bands, but I don't know how far it would move. When you put those dowels in between the floor and the car and all of a sudden lit it, what'd you notice? Well, I think I even saw some of the cars going over a meter long. Okay, so that's going to be rolling friction when you put something in between the two surfaces. If I take a ball and I drop it to the ground, well, what's causing it to fall? Well, I'm hoping all of you said gravity. Force that pulls all objects towards the earth. That's going to be what a gravitational force is. On Earth, there's two things I want you to know. Number one, I want you to know the negative symbol. Okay, on an XY axis, negative acts downward. And the other thing, here's the numerical part, 9.81 meters per second squared. So the value of Earth's gravity is going to be a negative 9.81 meters per second squared. Free fall is going to be when the only force acting is gravity, meaning there is no air resistance at all. Okay, so free fall, only gravity is pulling it downward. Well, let's look at an object that's going to be falling for 5 seconds, and that's in free fall. Okay, obviously if I'm holding it, time 0, we're not going to have any movement at all. 1 second goes by, we're negative 9.81. Second goes by, we're now 9.81 more than we were before. Third second, we're now 9.81 greater than that, so we're now at a negative 29.43. Time 4, negative 39.24. And finally, time 5, negative 49.05. Hopefully you figured out that if I just took 5 times that negative 9.81, I got the value that it would be moving at. Putting it in numbers that we'll understand, if something could go for 5 seconds, 1001, 1002, 1003, 1004, 1005. In that 5th second, it would have dropped and be moving at a rate of about 110 miles per hour downward. Projectile motion. Okay, here's something that I want you to think about. I'm going to take something and I'm going to throw it perfectly horizontal. At the same time I release it horizontally, I'm going to let something just fall downward. Which one hits first? Well, if you look in your book at figure 11, they hit at exactly the same time. The minute I release something horizontally, you're going to find out the only thing affecting it is gravity. The minute I take something and I let it go or let it drop, the only thing affecting it is gravity. And if gravity is going to be pulling it down, it's going to pull it down at exactly the same rate, causing them to hit at exactly the same time. So if all objects are accelerated by gravity, does that mean every object's going to hit the ground at the same time? Well, no. We know that's not true. If you take a hammer and a feather and drop them at the same time, you're going to find out that that hammer hits the ground first. The reason why? Well, number one, it goes back to Newton's first law with inertia. Okay, the hammer has more mass. The feather, it's a lot lighter. Okay, it's going to pick up that air a lot sooner than that hammer is. Air resistance is a specific type of fluid friction, and it's going to be pushing or cause air to push against an object. Well, I know air resistance or that fluid friction. You're driving down the road, roll down the window sometimes, stick your hand out. You're going to find that your hand goes backwards. It's that air that's going to be pushing against your hand. Terminal velocity, now that's in the presence of air resistance. What it is it's the maximum velocity that an object will reach during free fall in the presence of air resistance. A hammer, it's going to pick up a greater speed, and it's going to have a lot higher terminal velocity than a feather. You drop that feather and then all of a sudden it slowly starts swaying back and forth because it's reached its terminal velocity sooner than that hammer. Down here at the bottom, if you end up going to this website, what it is it is some footage. It's from Mythbusters, but it is some footage from when they did this experiment on the moon. On the moon, there is no air resistance. Okay, there's no atmosphere, there's no air up there. So with that being said, they ended up taking, I think it was a hammer and a feather in this video, and they go ahead and drop them, and both of them hit the moon's surface at exactly the same time. Let's go back and revisit weight and mass. Mass was going to be one of those things that we said was going to be the total number of particles in an object. On the other hand, we have weight, which is going to be the measure of an object's pull down because of gravity. Weight, as I said, it is a measure of that gravitational pull acting on an object. Really, weight is going to be a special type of Newton's second law. Newton's second law was force equals mass times acceleration. Well, this is going to be weight equals mass times gravity. Looking at the formula, this is not a negative sign here. Okay, that's just my hyphen, but it says weight equals mass multiplied by gravity. If we go ahead and we look at this here, okay, going ahead and drawing up a circle equation, here's what it's going to look like. Okay, there's our weight. Here's going to be our mass, and here's going to be our gravity. Now I said mass, okay, mass is still going to be in kilograms. Here's our gravity. If it is acting on Earth, okay, it's going to be a negative 9.81 that we end up putting here. And then weight is a special type of force, so this will end up being newtons. If we're on the moon, remember, moon's gravity is about 6 times less. So we would take gravity divided by 6. Okay, so let's go through our units again. Mass is in kilograms. Gravity is in meters per second squared. Weight will end up being in newtons. When we talk about the universal law of gravitation, okay, what they did is they took an experiment to the moon, okay, or actually in outer space. And what they did is they said, well, if all objects are attracted towards the Earth, what about any two objects? So what they did is they went into space and they took like 2 hammers and they hung them together. And on Earth, of course, we'd see those hammers hanging straight up and down. But when they went into outer space, they found out that those hammers actually bent a little bit towards one another. And what that started saying was any two objects are going to be attracted towards one another. And that's stated in that universal law of gravitational force. Okay? There's going to be 2 factors that attractive force are going to depend on. Number one is going to be the mass of the objects. Heavier objects, more gravitational force or more attractive force. And the second one is going to be the distance between those objects. As I said, heavier objects, they're going to have more of an attractive force, thus saying mass and force are going to end up being directly related to one another. The closer objects are, like if I bring two objects closer together, there's going to be more attractive force between them. So if we're saying objects get closer, that means distance goes down, that gravitational force or attractive force goes up, meaning that distance and force are going to be indirectly related to one another. The last section is going to start talking about centripetal force. And the first thing we're going to do is we're going to look at satellites. And a satellite is just going to be any object that travels around some other object in space. For example, the moon. It is a natural satellite of the Earth. The moon travels around the Earth. The Earth, it's a natural satellite of the sun as it moves around the sun. If we talk about military satellites, these are man-made satellites. We go ahead and we put them above the Earth, and as they are traveling around the Earth, these are man-made satellites. So it's any object that's going to travel around another object in space. I talked about weather, military intelligence, communications that our cell phones are going to operate off of. These are all satellites that we put into space. The satellites in space are constantly orbiting the Earth. But what keeps them from flying off? I mean, they're trying to go in a straight line, and they can't. They just keep circling the Earth. Well, the reason is because of Earth's gravity. As they're trying to fly straight off into space, Earth's gravity pulls them back down, or pulls them in that circular motion. As an object moves in a circle, there is a force acting on it that keeps it moving in that circular motion, and that's going to be centripetal force. It's a force that causes an object to keep moving in that circular path around the object that it is orbiting. As I said, moon moving around the Earth, Earth moving around the sun, these man-made satellites moving around the Earth. Here's the key thing. It is directed towards the center of the circle, or it is directed towards the center of the object it is orbiting. So if I go ahead and I draw a little circle up here, okay, and we're going to say that this is the Earth right there in the middle, okay, and we're going to say that this is a satellite right out here, okay. Well, all of a sudden, centripetal force, what it's going to do is it's going to be directed towards the center of the Earth, okay. If it's up here, you're going to find out that it's going to be directed down there, okay. If we're out here, it's going to be directed in towards there. So it depends on where it's at, on the direction it's going to be directed, but it's always safe to say centripetal force is always directed towards the center of the object that it is orbiting. So as that moon goes around the Earth, the centripetal force is going to be directed towards the center of the Earth. As the Earth moves around the sun, it's going to be directed towards the center of the sun. Your assignment is going to be to read pages 323 to 329. This is the frictional stuff. Pages 338 to 340, that's the centripetal force stuff. There's 4 questions on page 329, and there's 4 questions on page 340.